Derek, Storey, and also by Pranav Pasari. So just to introduce them, Derek is Head of Integrity Services at Inspipe Integrity Limited. He has held senior positions over the last 40 years with several leading service companies supplying inline inspection and integrity management solutions to pipeline operators globally. His early career was in research physics, working on ground-penetrating radar systems and other electromagnetic technologies for the British Gas Engineering Research Station in North East England. He was a member of the original team that developed the world's first high-resolution MFL inspection, inline inspection technology. This technology ultimately formed the basis of the accepted standards for all metal loss inspection. And then the other presenter today is Pranav Pasari. He is Director of Technology at Satsense Solutions Limited, having previously worked in technology consulting. He is responsible for developing business applications using satellite Earth observation data and has several years' experience working with satellite remote sensing data products and software. He has an MSc in Systems Engineering from the University of South California. So over to Derek and Pranav. I look forward to your presentation.
Thank you, Diane. Can you hear me okay?
Yes, loud and clear.
Okay, that's great. Well,
thank you, Diane. It's a pleasure to present here today.
Okay. Well, good day, everyone. It's a great pleasure to be presenting here today. I am Derek Storey, and I am Head of Integrity at Inspipe Integrity Limited, a company that specializes in advanced ILI systems and integrity management solutions. Today, I will be presenting, along with my co-author Pranav Pasari, a summary of a joint development initiative that was aimed at improving the effectiveness of geohazard management in pipelines. The following slides represent a summary of our joint development initiative to measure pipeline strains by a two-method NDT approach. The project followed from an initial contract with the pipeline operator to perform a baseline geometry inspection of a newly constructed 28-inch diameter pipeline. Following the baseline survey, the project went on to study possible pipeline strains induced by ground movements in a seismically active region of Sumatra. As well as seismic issues, the subject pipeline was perceived to be vulnerable to additional geohazard threats arising from mining activities. So this is the region. And on the left-hand side, in the left-hand graphic, you can see the root cause of the seismic activity in the Indo-Australian region. The Indian and Australian tectonic plates are physically fused at the boundary. So they exhibit no relative movement to one another. The whole of this fused Indo-Australian tectonic plate is moving northward, but at different rates for the eastern and the western parts. The Australian part of the plate moves north at 5.6 centimeters per year, but the Indian part of the plate over here moves north at only 3.7 centimeters per year due to the huge impediment of the Himalayan mountains in India. The difference in plate movement rates causes enormous plate stresses to develop along the entire 1,790 kilometer length of the Sumatran west coast. And the effect of these stresses can be clearly seen in the right-hand graphic, which shows the long line of active volcanoes running all the way down the western seaboard of Sumatra. Stress releases in the colliding tectonic plates result in earthquakes, and some of these exceed magnitude 9, very serious earthquakes. Earth movements can, of course, displace pipelines, and thereby induce abnormal pipeline strain. So this project was really looking at a different method of looking for pipeline movements in the induced strains. This slide shows the 28-inch diameter high-resolution geometry tool being received in excellent condition. The tool was fitted with a high-definition inertial measurement unit, or IMU, which measured the precise 3D location of the pipe center line as X, Y, and Z coordinates. And IMUs fitted as standard to most Inspipe geometry tools in order to improve the identification of pipeline features such as wells. The combination of a high-resolution geometry tool with a high-definition IMU system is not really common in the industry for a variety of reasons. This is showing a close-up of the geometry tool in the receive tray. The sensors can be clearly seen on the right-hand side there. There are 56 of them, and they're capable of measuring a 1 millimeter variation in the diameter of the pipe. And they're all running on wheels to provide a smooth transit over the pipeline internal surface. In slide 5, we see in the top graphic a table of the most significant geometry features that were found in the pipeline. There is nothing of concern to the integrity of the pipe here. They all relate to bore reductions that arise from perfectly acceptable construction features. And in every case, there is no adverse effect on the integrity of the pipeline. The threshold set for listing geometry features was 3% of the ID of the pipe for reductions, dents, ovalities, and so on. The bottom graphic shows a table of the IMU strain results. And this data was analyzed to identify strain features that exceeded for more than one pipe joint and which had a peak value exceeding 0.2% strain. This excluded bends and angular misalignment at girth welds. 5 bending strain areas on the left shown as BS1 to BS5, which met the criteria, were identified, all of them in the vertical plane. All of these features were attributable to misaligned girth welds, and their details are given in the table. The maximum total peak strain was calculated to be 0.33%, and that is designated as BS1. This graphic is showing as a function along the pipeline the various parameters associated with BS1. On the top, we see the height above sea level. The very important strain graph is shown the next down, and at the bottom are pitch and azimuth outputs. The effects of noise can be clearly seen on pitch and azimuth. And special processing is required to minimize the adverse consequences of this is due to vibration. We have to use special processing to minimize the results of vibration. The key graph, of course, is for strain, which is the second down here, and it shows the total strain plotted as a function of distance along the pipeline, and it clearly shows the peak strain lying between 2 girth welds here. At this point, I'll hand over to my colleague Pranav Pasari, who will continue with this presentation.
Thank you, Derek. Thank you, Derek, for covering the first part of the presentation so well. Could you go to the next slide, please? So before we get into the technical details and results of the satellite-based ground disturbance analysis, I would like to present a brief overview on the concepts and the technology used. Satellite remote sensing is the use of space-bound sensors to monitor activity and changes on the ground. In this case, activity and changes near our pipelines. In this case, we use synthetic aperture radar, also known as SAR, and interferometric SAR processing techniques to detect ground disturbances between specific time periods. This system allows for accurate measurement of the radio wave path and can therefore provide centimetric and millimetric surface deformations of the terrain. This is illustrated in the diagram on the screen. While measuring changes in ground displacement, we note that there is a difference in travel path between time period A and time period B, indicated here as phase difference. Very simply stated, this difference is calculated to measure the ground displacement between these two time periods. Derek, next slide, please. As you may know, geohazards are one of several leading causes of pipeline distress. This slide presents an overview of the different types of geohazards that impact pipelines. Geohazards can be commonly categorized into these four groups. The first group is seismic, a common example of which is faults. The second group is geotechnical, common examples of which are landslides and subsidence. The third group is hydrotechnical, flooding of which is a common occurrence. And the fourth group is erosional hazards, an example of which is right-of-way washouts. While this paper addresses only the impact of ground disturbances due to seismic and geotechnical phenomena, we will be showing examples of some of the other categories as well. Next slide, please. Presented here is a schematic for the different types of satellite remote sensing analyses we can use to assess specific geohazards. In this paper, we perform the ground disturbance analysis that looks at both seismic and geotechnical geohazards. Pipelines are especially susceptible to ground disturbances due to the long linear nature of their paths that may pass through afflicted areas. Ground disturbances can cause displacement of pipelines as well as longitudinal, tensile, and compression loads. Next slide, please. In this slide, we would like to show you some examples from other projects of the different types of geohazards and how they impact pipelines. At the top, we see an example of hydrotechnical hazards in the form of channel migration or river meandering. In this case, we see the river channel interaction with the pipeline as it changes path in 2010, 2014, and 2019. We can see that in 2010, the river was particularly active, crisscrossing the pipeline at several additional locations. On the example on the right, we see an ROW washout, where soil over the pipeline has been washed away due to heavy rains. On the left, we see an example of seismic activity from a swarm of 55 low-intensity earthquakes within a period of 1 year that caused ground subsidence of 2.8 to 5.6 centimeters. The impacted pipeline was around 1.5 kilometers away from the epicenter. Next slide, please. So coming back to the current paper, if you recollect, Derek had highlighted 5 bending strain areas identified from the IMU analysis. The locations of these are seen here in red dots. BS1 near a riverbed is seen on the image on the left. BS2 through BS5 are seen from left to right in the image on the right near the coal mine. BS4 and 5 seen in the right-hand corner seem to be some distance away from the main coal mine and hence seemingly away from possible geohazards. They are in fact very near coalbed methane wells, as can be seen from the satellite imagery. Therefore, the pipeline in this area may still be impacted by geotechnical ground displacements caused by drilling and water pumping occurring here. We shall see results of the ground displacement analysis and how it pertains to these points in the next slide. While BS1 may have been impacted by hydrotechnical phenomenon, this has not been evaluated as part of this project. Next slide, please. In this slide, we see the results of the ground displacement analysis performed using satellite SAR data and interferometric SAR processing techniques. This analysis was performed for the time period between August 2016 and August 2018. This was done to coincide with the IMU survey that was performed in early September 2018. The ground displacement data is extracted for points corresponding to the IMU survey and provided in a tabulated format as seen in the table. A strong correlation was found between the 5 bending areas and the ground displacement analysis performed here. It is worth noting that ground displacement near a pipeline can manifest very differently as stresses and strains on the pipeline, depending on local conditions, pipeline construction, design factors, etc. Therefore, satellite-based analyses alone are not sufficient to gauge the specific impacts of ground disturbance on pipelines, but they can act as an important first screening tool for these kinds of geohazards. In the image on the right, we see satellite-derived ground displacement visually represented along the coal mine and the pipeline sections. We can see that these displacements vary widely from 6 centimeters to 12 centimeters along the pipeline section. I would like to hand it back to Derek to conclude on the presentation. Thank you.
I hope everyone can hear me okay. So, conclusions. This project successfully evaluated an integrated 2-method approach to the measurement of ground movements and other geohazards near a pipeline. Based on a combination of IMU and SAR data, small ground movements were used to calculate bending strains in ground disturbed areas. While no structurally significant pipeline strains were found, the project clearly confirmed the value of integrating IMU and SAR data to increase the confidence of the data analysis. As anticipated, dense forest cover led to signal coherence loss in some areas due to dispersal of the radar signal by the forest canopy. Despite this, results were highly encouraging. Further development of the combined IMU-SAR methodology is already underway in a partnership between Inspipe Integrity Limited and Satsense Solutions Limited. Future work will refine the methodologies and the technologies involved, including analysis of historical data for each method to enhance the predictive capabilities of the integrated analysis. And I thank you for listening to the presentation, and I guess we're ready for questions now.
Okay, thank you, Derek and Pranav. Very interesting presentation there. Yes, we're opening up to questions. If anyone's got anything they'd like to ask. There's nothing on the screen yet, but we'll just give it a few moments. Oh, one's come in, right, from Brian Mellon. Hi, Derek, nice to see you. It's been quite a few years. What is considered a structurally significant strain for a pipeline?
That's a very good question, Brian. And I think that first of all, I should say that this was a trial project. This trying to evaluate the methodology involved. I'm not sure that strain on its own is a parameter which is used in determining structural significance. It's really about the way in which the strain is interfering with other things. Pipelines can move quite a large amount, and I think that a detailed fracture mechanics calculation will be needed to determine whether or not integrity was affected. I used the expression insignificant effect on integrity for the purposes of this presentation, but there's really a lot that lies behind this. I'm not aware, maybe somebody else can indicate, but I'm not aware of any codes or regulations which list specific strains as being a parameter which determines good integrity or bad integrity.
Okay, thanks, Derek. Any other questions for Derek and Pranav? Otherwise, as usual, if you think of any after the presentation, then obviously you'll be able to contact them direct, and I'm sure they'd be happy to answer anything that you have. So yeah, I'd like to just thank you very much. Very clear, very interesting presentation. And again, appreciation I'm sure is coming from around the world to you both.